Hi everyone, welcome back to Lulumath. This video is on solving word problems with linear equations, and we will be looking at distance, rate, time problems specifically in this video. And the background knowledge you'll need is how to solve multi-step equations, and you can find that at lulumath.com as well as the Lulumath YouTube channel if you'd like a refresher before you watch this video. And there's also a general word problem video at lulumath.com as well, where we kind of go through a process of what we need to do in order to problem solve and critically think through these types of examples. And so I'll still follow that process as I go through this specific type of word problem. So if you want to check that out as well, feel free to if you feel like that will be helpful to you. We also have some other specific word problems as well if you'd like to check those out. So the first thing we want to do whenever we attack a word problem is we want to identify key information. So looking at the problem, it tells us that a bus leaves a station and drives at an average speed of 75 kilometers per hour. Then 30 minutes later, so that's important, another bus leaves the same station and drives in the same direction at an average speed of 100 kilometers per hour. How long will it take for the second bus to catch up to the first bus? So the next thing we want to do is identify what we want to know. And what we want to know is how long will it take for the second bus to catch up to the first bus? Then we need to draw a picture of what's happening. So sometimes we skip this step, but in this example, it's going to be really important for us to draw a picture so we know what's going on. So we know that bus number 1 starts driving at a rate of 75 kilometers per hour. And we know that bus number 2 starts driving a half an hour later after bus number 1 starts driving. So bus number 1 has reached a point right here when bus number 2 starts to drive. But because bus number 2 is driving faster, it's going to eventually catch up with bus number 1. So this right here is where bus number 2 will end up catching up to bus number 1. So they will have covered the same amount of distance. We're going to add to our picture after we get to step number 4, which says to write specific let statements. Now, when we write our specific let statements, we always ask ourselves, what do we not know? But I'm also going to use this table here to help us sort through our information because this is going to help us out. What we don't know is how long it will take for the second bus to catch up to the first bus. So the amount of time is what we don't know. So we always write that as our let statement. And if we don't know the amount of time, we're going to just call it T. So we're going to sort through our information here, but I just want to remind you a really important equation, and that is that distance is equal to the rate times the time. And this is something that you naturally do. So like, for example, if you go on a walk and you're walking at a rate of 3 miles per hour and you go for an hour, then you have gone 3 miles because 3 times 1 is 3. Or if you go for 2 hours, then you've gone 6 miles because 3 miles per hour for 2 hours, 3 times 2 is 6, okay? Quick note, make sure that the rate or the speed is the same unit as the distance as well as the time. So the rate or speed would be miles per hour. That means the distance has to be measured in miles and the time has to be measured in hours, okay? So let's sort through our information here. We have bus number 1 and we have R here, which stands for our rate. And we know that that bus number 1 is going at a rate of 75 kilometers per hour, okay? We don't know how long bus number 1 has gone for, so we're going to call this T, but this time has to be in hours, okay? Because this is 75 kilometers per hour. Now, since distance is equal to the rate multiplied by the time, we don't know the distance, but we do know that in terms of T, the distance is going to equal the rate, which is 75, times the time. So D equals RT. Just a reminder that that's where we get that from. So we know that this total distance from here to here is 75T. Now let's talk about bus number 2. So bus number 2 starts leaving a half an hour later at a rate of 100 kilometers per hour. So we know that bus number 2's rate is 100. But the amount of time that the bus is spent driving is not T because they go a half an hour later. So just a reminder that 30 minutes is equal to half of an hour. Okay? So the total time that bus number 2 is actually driving for is half an hour less than the total time that bus number 1 is driving for. We can take bus number 1's time and subtract that half an hour because again, it's a half an hour less or 0.5 hours less. Making the distance being rate times time, the rate is 100. And then the time is this t minus 0.5, but we have to put this in brackets because it's 100 multiplied by the full time, which is t minus 0.5. So we know that the total distance that bus number 2 has gone is equal to 100 times t minus 0.5. And we'll call this D2 for bus number 2's distance, and we'll call this D1 for bus number 1's distance. Well, they start at the same spot and they will catch up at the same spot, which means that the distances are equal to each other as shown in our picture here. So we know that D1 is going to equal D2. So therefore, we can say that D1, which is the 75t that we have here, is equal to D2, which is this 100 times t minus 0.5 that we have here. And just a reminder that we also have it here and here. All right, so we've gone to the point where we wrote our specific let statements. Awesome. We wrote our equation. Now we have to solve our equation. So I'm going to copy down this 75t and I'm going to distribute the 100 through to both of these numbers here. So I get 100t minus 50. I'm going to subtract this 100t from both sides because it's a positive 100t. Just a reminder, this minus sign is for the 50. And when I subtract 100t from 75t, I get negative 25t. And then I have negative 50 left over. Divide both sides by negative 25 and I get t equals 2. So I know that the amount of time here is equal to 2 hours. So here I can say t equals 2 here, and then here I can say t equals 2 minus 0.5, so it's equal to 1.5. So let's go back into our picture and see how this is going to help us out. Well, if D1 is equal to 75 times t, I can do 75 multiplied by the 2, we know it's 2 hours, and when I multiply those two numbers together, I get 150 kilometers. Now for D2, it would be 100 multiplied by t minus 0.5, which we figured out was this 1.5 right here. And when I multiply 100 by 1.5, I get 150 kilometers. And they're equal to each other, which is what we want because they will have traveled the same amount of distance. So now we want to answer the question. And the question is asking us, how long does it take for the second bus to catch up to the first bus? And we know it takes the second bus 1.5 hours to catch up to the first bus. Making this our final answer. But don't forget that we always want to ask ourselves if our answer makes sense. So first of all, is 1.5 hours an answer that would make sense for a bus to be driving? Absolutely. If we end up getting negative 72 hours or some crazy irrational number, then we would want to think, maybe something's not right here. Our answer also makes sense because we know that both buses have traveled 150 kilometers, which is required in order for us to make sure that we did this correctly. So we did it right and we are good to go for this question. Okay, in our next question, we want to identify our key information to start off with. So an airplane flew from one city to another at a rate of 900 kilometers per hour, okay, and it's from one city to another, so that's important. And then the airplane flew back at a rate of 720 kilometers per hour. The total trip took 13.5 hours, and we want to know what is the distance between the two cities. So now we're going to identify what we want to know, and what we want to know is the distance between the two cities. Now we're going to draw a picture if necessary, and here it will help us to visualize what's going on. So we have our first city, which I'll call City A, and then we have our second city, which I'll call City B, and we know that the airplane went from City A to City B right here in a certain amount of time. We don't know how long that time is specifically, just going in one direction. We know the total trip, but we don't know from City A to City B. This is the airplane going. Then the airplane returns from City B to City A. So it starts at City B and then it returns to City A. And we know that the total time that it took was equal to 13.5 hours. Now we want to write our specific let statements. So we don't know how long it took for the plane to go, and we don't know how long it took for the plane to come back. So if we don't know the time to go, and we're measuring this in hours, if we don't know the time it took to go, we'll call it T. Here's where we want to be careful. That means that the time returning or coming back, we're not going to call it a new variable, but we know that the total time is 13.5 hours. So let's say, for example, even though this is not the right answer, but let's say, for example, it took 2 hours to go. That means that coming back will take us 11.5 hours because 2 plus 11.5 is 13.5. Well, how do we get that? We did 13.5 minus 2. Well, let's say it took 4 hours to go. Then that means that it would take 9.5 hours to come back because 13.5 minus 4 is equal to 9.5. So our issue is that we don't know how many hours it took to go, which is why we called it T. So for how long it takes to come back, instead of 13.5 minus 2 or 13.5 minus 4, it's 13.5 minus T. So that will be our let statement for our time returning, okay? And we're going to organize all of our information here in our chart. So going, we know that the plane was flying at a rate of 900 kilometers per hour. And we know that the time, we called the time going, is called T. So because distance is equal to rate times time, and because our rate is 900 and our time is T, we're going to say that our distance is equal to 900 T. Now for the plane, when it's returning, we know that the plane was flying at a rate of 720 kilometers per hour, and we figured out that the returning time is going to be expressed as 13.5 minus T. And so when we do our distance equals rate times time, we're going to say that it is 720 multiplied by 13.5 minus T in brackets because this whole entire expression represents the time. So we need to have brackets or parentheses here. So we know going that our distance is going to be equal to 900 T. We have that right here. And we know that returning, our distance is going to be equal to this 720 multiplied by the quantity 13.5 minus T. And because the airplane is going from city A to city B on the way, and then going from city B to city A on the way back, we know that the distances are equal to each other. So we can say that this 900T that we see here, and that we also see here, will be equal to this distance that we see here, or the one that we have written here. I always forget to get to this point where we say we want to write our equation. I just jump right into it. And that's how amazing the let statements are, because they just help us get right into writing our equation. So we're done with step 5. We've written our equation. So now we want to solve our equation. So let's go ahead and do that. So I'm going to copy down this 900T. So when I distribute 720 to 13.5, I end up getting 9,720. And then 720 multiplied by negative T is negative 720T. Well, I'm going to get rid of this minus 720T by adding it. And whatever I do to one side, I do to the other side. So when I add 720T to 900T, I end up getting 1,620T is equal to 9,720. Now I'm just going to divide by 1,620 and I get T equals 6. I divide both sides by, so here we know that this total time right here is going to take 6 hours, and here we know that this total time is going to take 13.5 minus 6, which is 7.5 hours. So we figured out how long it's going to take for us to get there and to return back. Beautiful. So now we've solved our equation. Our next step that we're going to look at is answering the question. And the question is asking us, what is the distance between our two cities? So we need to use these two expressions here or these two expressions here. And they better be equal to each other because the distance between the two cities, regardless of whether you're going or coming back, should never change. So going, we have this 900T, and we know that T is equal to 6. So when I multiply 900 by 6, I get 5,400 kilometers. So at this point, we can stop. We've got our answer, but I want to double check to make sure that we did this right. So I'm going to use the returning distance and see if we got it right. So D equals 720 times 13.5 minus T. And we know that it's going to be 13.5 minus the 6 that we got. So I end up getting D equals 720, and we already figured out that this should be 7.5. And when I multiply 720 by 7.5, I end up getting 5,400 kilometers. So they're equal to each other, which is perfect because that tells us that we did this correctly. So we can say, therefore, the distance between the two cities is 5,400 kilometers. So now we want to ask ourselves if our answer makes sense. Does it make sense that the cities could be 5,400 kilometers away from each other? Absolutely, it could make sense. They're pretty far from each other, yes, but it's still possible. And a time of 6 hours and a time of 7.5 hours also makes sense. So we are good to go with this question. All right, in our last example here, we're going to, again, identify our key information. So Noah and Liam met up for lunch one day. When they were done, they started walking at the same time in opposite directions, and Noah walked 1.5 kilometers per hour faster than Liam. After 2 hours, they were 22 kilometers away from each other. And we want to figure out, so we identified our key information, we want to figure out what we want to know. So we want to know how fast each person walked. The next thing we're going to want to do is draw a picture if necessary. And drawing a picture here is definitely going to help us understand what's going on. So here we know that they started in the same spot. And we know that they walked in different directions. So we have Noah walking one direction. And we have Liam walking another direction. And we know that Noah walked 1.5 kilometers per hour faster than Liam. So I'm actually going to combine writing our specific let statements with our picture when we do this, because this is going to help us out if we kind of consolidate it together. So here we have Noah and here we have Liam. And we always ask ourselves, whenever we write our specific let statements, we always ask ourselves, how many things do we not know? So we don't know how fast Noah walked and we don't know how fast Liam walked. But we also ask ourselves, what is everything based on? So Noah walked 1.5 kilometers per hour faster than Liam. So that means that Noah's rate is based on Liam's rate. And if we don't know Liam's rate, then we have to write a let statement for that. So we're going to say let Liam's rate. And if we don't know it, we'll call it R. Okay, so here Liam's rate is R. Well, we know that Noah walked 1.5 kilometers per hour faster than Liam, so we're going to write a let statement for Noah's rate. So we take Liam's rate and we add that 1.5 kilometers per hour faster. So I'm going to put this in our chart right here. Now for our time, we know that this is 2 hours right here. So we know that our time is going to be 2. So we don't have an unknown for our time this time, which is nice. And just a reminder that our distance is equal to the rate times the time. And the beauty of multiplication is we can do rate times time or time multiplied by the rate. So for Noah's expression for distance, I would take the rate and multiply it by the time. But I'm going to put the time first because it's a constant and it's a single monomial. And I'm going to multiply that by the rate in bracket because it is 2 multiplied by all of Noah's rate, which is R plus 1.5. And I'll do the same thing for Liam. So I'm going to take the rate and multiply it by the time, but I want that 2 in front as a coefficient, so I'm going to say 2R. So we know that Noah's distance here is equal to 2 times R plus 1.5. And we know that Liam's distance here is equal to 2R. And we know that the total distance between the two is equal to 22 kilometers, right? We are told that after 2 hours, they're 22 kilometers away from each other. So this picture is really going to help us to get to our next step where we want to write our equation. So to help us write our equation, we know that Liam's distance and Noah's distance combined together will equal 22 kilometers. And we know that Liam's distance is 2R. We're going to combine that with Noah's distance, which is this 2 times the quantity R plus 1.5. And we know that that's going to equal 22. So let's go ahead and solve this. I'm going to copy down this 2R, and then I'm going to distribute the 2 through. So 2 times R is 2R, and then 2 times 1.5 is 3, and then I'm going to copy down this equals 22. Okay, and then I'm going to collect my like terms. So 2R and 2R together give me 4R. Copy down this plus 3, and that's going to equal 22. I'm going to subtract the 3 from both sides, so I end up getting 4R equals 19. Divide both sides by 4, and I get R equals 4.75. So we know that this rate is equal to 4.75 kilometers per hour. which means that Noah's rate has to be 4.75 plus this additional 1.5. So we know that Noah's rate is going to be equal to 6.25 kilometers per hour. So now we can get to a point where we can answer the question. And the question is asking us, how fast did each person walk? And our answer is here and here. So we can write our therefore statement. So therefore, Liam walked at a rate of 4.75 kilometers per hour, and Noah walked at a rate of 6.25 kilometers per hour. All right, everyone, one last thing we have to ask ourselves. Does our answer make sense? So let's see. If Liam walked for 2 hours at a rate of 4.75 kilometers per hour, then Liam walked a total of 9.5 kilometers. And if Noah walked for 2 hours at a rate of 6.25 kilometers per hour, then Noah walked for 12.5 kilometers. And when I add 9.5 kilometers and 12.5 kilometers together, I end up getting this total of 22 kilometers, which means that our answer makes sense. It also makes sense that I could get 4.75 as a rate or a speed. Okay, and that's it for this video. If you have any questions, let us know in the comments below or at lulumath.com, where you can also find blank or completed notes for this video. If you found this video to be useful, please make sure to subscribe and share with others. Thank you, and we'll catch you next time. Bye.